I'm Jesse Chan. This is the slide title, and all of this work should be given credit to Yimin Lin, my PhD student who just defended his PhD. So, in the end, what we want to do is do nice high order accurate CFD on unstructured meshes, which I know is of interest to many folks here. And for really technical reasons, I'm interested in using discontinuous Galerkin methods, mainly because they give us geometric flexibility. They can deal with these unstructured meshes, and they make going to high order relatively easy. They also have a structure similar to finite volume methods, which will end up proving crucial for some of the things that we want to actually demonstrate. So if you've heard of DG methods, you have probably heard of a lot of people giving lots and lots of complicated reasons for wanting to do DG methods. They are good for HP adaptivity, or they're stable for advection problems, et cetera, et cetera. I think a lot of this is a little hard to actually quantify. Really, what I use DG for is explicit time stepping. Makes it very easy to do explicit time stepping for finite element method compared with high order finite elements. So if you have a high order finite element scheme, then generally speaking, what you have to do is invert a mass matrix at every step. It's globally coupled but sparse for a high order finite element scheme, and completely block diagonal and trivial to invert for a high order DG scheme. So this is really my motivation for discontinuous Galerkin, but what I want to focus on in this talk is more about high order accuracy. And this is a slide that I've adapted from several people before, where it's just illustrating if you take the advection equation and rotate a Gaussian wave around and around and around about 5 times, then what you see is for a first order method, if you have something like an upwind finite volume scheme, then you dissipate away almost all the information. If you do a second order reconstruction, you get some resolution back, but it still dissipates away the peaks. Fourth order improves things even more. Eighth order improves things even more to the point where you can't tell the difference between the exact and the approximate solution. And what you'll notice here is that we're actually using far fewer elements on this coarse 8th order mesh so that we have exactly the same number of degrees of freedom throughout all of these 4 plots. So this is a promise of high order accuracy, that you can really accurately get propagating waves and vortices. And while this is just a simple 1D advection equation, it's not too hard to imagine that something carries over to more complex problems as well. So if you have the Taylor-Green vortex, just simple periodic turbulent-like behavior in a box, the second order DG scheme on the left shows a lot of numerical dissipation. You can see a lot of artifacts that look like discontinuities in between different cells. If you bump up to fourth order, then things look already a lot better. If you are a little bit crazy and decide to go to 16th order, then you get this result from Beck and Gassner in 2013, which shows an incredibly nicely resolved Q criterion structure for the Taylor-Green vortex. This is the promise. This has been the promise of higher order methods, I think, since nearly the 80s. And what often ends up being an issue is, well, why don't we actually use these in practice? Often because these higher order methods, while they're incredibly accurate, are much less stable. So here's an example of the Burger's equation. You have the exact solution on the left, and after you run this for a certain amount of time, it develops a discontinuity. And if you have a higher order DG method, 8th order on the right, then you can see that this discontinuity, if it cuts through a cell, develops oscillations. So if these oscillations are not damped down using some other filtering or artificial viscosity or limiting method, then they'll eventually oscillate and grow and blow up and cause your solution to crash. And this was the issue that I ran into for several years before I stumbled onto my current area. In general, what happens here is if you have under-resolved solution features, then this results in instability in naive implementations of high-order DG methods, which eventually led me to look at these entropy stable schemes. So to try and illustrate why I'm interested in this, you can, of course, run a high-order DG method without actually needing to resort to entropy stable schemes. But typically what you will do is you'll add some sort of heuristic stabilization. Artificial viscosity, filtering, and all these things are fantastic. They're really necessary for real world problems. I don't want to diminish them. But if you rely solely on these, I found that things to be a little bit tricky because in my postdoc advisor's book, you have this nice little quote. When working on nonlinear problems, to combat this instability, it was recommended that you apply filtering to apply as little as possible, but as much as is needed. And that sounds reasonable. Don't over dissipate to reduce accuracy, but don't under dissipate and to the point where you don't get stability. But knowing where exactly that line is really tricky. And there are some modern schemes which do a much better job of figuring out where exactly to stop this filtering. But for a lot of the existing stabilization methods, when I started this work, it was hard to tell where the line was between as little as possible and as much as needed was. So the idea behind these entropy stable schemes is that they should improve robustness without actually adding dissipation to provide a fundamentally different stabilization mechanism. And while it doesn't turn your DG method into a bulletproof method, I would say it turns it into a quote unquote good high order method, something akin to something like a second order finite volume scheme. So let me just give a quick motivational slide. All of these are images from different groups. This is from my group. This is from, actually, I guess these two are from Parsani's group. There are a couple other images that I used to flash up, but all of these are entropy stable, out of the box, high order DG simulations. So here and here, I believe these are fourth order. This is something like an eighth order scheme. You have Kelvin-Helmholtz, you have flow over a cylinder with some shocks and some waves coming off of the wake of the cylinder. And all of these are run completely out of the box, no artificial viscosity filtering or slope limiting. So at least these aren't the most challenging problems, but the fact that we can run things without having to apply any additional stabilization made me interested in these high order entropy stable DG methods. So what I'm going to try and do is explain a little bit about what entropy stable nodal DG methods are. I'm going to assume this nodal assumption in this talk because it allows me to also develop positivity preserving limiting schemes for these nodal DG methods. I'm also going to talk finally at the end about an extension where we actually try to reverse, where we combine limiting with symmetry inequality to get a new set of entropy stable schemes. So let me start by talking about what these entropy stable nodal DG schemes actually look like. And I'm going to start by trying to outline some of the general theory. So we're interested in nonlinear conservation laws, possibly with some parabolic or incomplete parabolic dissipation terms. So if you have Berger, shallow water, compressible Euler, Navier-Stokes, all of these fall into this general framework where we have some nonlinear conservation law, du dt plus some the derivative of some nonlinear flux is equal to either 0 or some dissipative term. So U, I'm going to assume, is always going to be the conserved variables. I want to be able to write my equations in conservation form. And if you manipulate this equation, you can end up showing a continuous entropy inequality. The way you derive this is going to be important for the development of our schemes. What we'll do is we'll assume that we have stability with respect to some convex entropy functional S, and then we'll compute a set of entropy variables by taking the derivative of this functional with respect to U. So since this convex functional is scalar, you take the derivative with respect to a vector of conservative variables, you end up with a second vector of variables, which we'll refer to as the entropy variables. And so long as this entropy function is actually convex, it's a one-to-one continuous mapping in between these two sets of variables. So if we take these variables, multiply our equation by them, do a lot of calculus and arithmetic, then you eventually end up with the following statement down here, which essentially says that the average rate of change of entropy over your entire domain plus what essentially amounts to the entropy flux in and out of the boundaries is less than or equal to 0. So since this entropy is a mathematical entropy, if you think in terms of physical entropy in a closed system should always increase. Slap a negative sign on that and you roughly get the mathematical entropy. And so the negative of the physical entropy is always decreasing. And that is our stability property. So what we're going to do is basically try to imitate finite volume methods as much as possible, because much of this theory for finite volumes was developed back in the 80s by Eaton Tadmore. So we take a standard first order finite volume scheme, then you can typically write them in the following way. If I have a semi-discrete system, I can evolve the ith cell average, u sub I, by basically setting this right-hand side equal to this difference in these numerical fluxes across cell interfaces, divided by h, where h is some uniform mesh size. This is the simplest finite volume scheme that you would try to teach to an undergrad, I think. And what is nice about finite volume schemes is if you change the definition of this numerical flux that couples together neighboring cells, then you get different properties. So what these entropy stable and entropy conservative schemes are based off of is the idea of an entropy conservative numerical flux in the sense of Tadmore. So these fluxes satisfy three conditions. The first two are fairly standard. The first one is consistency, which is just if you evaluate this flux at both states, you get back the regular fluxes for accuracy. The second one is for symmetry. This is for conservation. We are solving conservation laws. And the third one is a conservation or an entropy conservation condition. And this one is the unique one to these fluxes. So if you take the entropy variables evaluated at some left state and some right state, and take their difference and contract that, dot that against the vector of entropy conservative fluxes when you evaluate at a left and right state, then the idea of an entropy conservative flux is that this gives you exactly the jump in what's known as the entropy potential. This entropy potential is some physical quantity. It's involved in the proof of entropy stability, but we're mostly going to ignore this. This is just some mathematical term that we need to set exactly equal to this left-hand side. If you have these three conditions, then you can show that this finite volume scheme conserves entropy, or at least it conserves a discrete analog of entropy. And if you slap a dissipation term on the right-hand side, then you get entropy stability. So this is our baseline. And these entropy conservative fluxes, they weren't previously known in closed form, but in about 2013, Chandrasekhar, Ismail and Rowe, and a few others developed closed form expressions for these entropy conservative fluxes. And just to show you, they look something like very weird central type fluxes. You have, if this is for the compressible Euler equations, you have something like the mass flux where you have rho times u, density times the velocity. That's relatively standard, but the actual averages used inside here involve these strange logarithmic averages. You have the product of this log average and u. You also have some strange variables like inverse temperature. We're not going to assume, we're not going to go much into detail about these entropy conservative fluxes. We will just assume that some closed form expressions exist and that we can access them. So the actual numerical structure is going to be based off of a reformulation using the Hadamard product. And what I'm going to do is take a periodic finite volume scheme down here and try and reformulate it in a Hadamard product structure so that it makes things easier to transfer to the nodal DG setting. So if we take our finite volume scheme on a periodic grid, then you can just write it in vector form as this following system down here. So we have the difference in entropy conservative fluxes across each interface. And what I will do is I will start to abstract this away. I'm going to instead write the scheme as the difference between fluxes, entries of a flux matrix, where this flux matrix is just this entropy conservative flux evaluated with different solution states on different cells. So now we have this matrix of flux evaluations between every single state in our finite volume mesh. And if we take this term on the left, this vector of flux differences, we can further write this using the Hadamard product in this form. So this is just an algebraic reformulation. Hadamard product is just the entry-wise product of two different matrices, what you wish that matrix multiplication was when you first learned it. And if you stare really closely at these two matrices, you have a flux matrix on the right. This captures the physics. And then you have something that looks actually like a discretization matrix on the left. And if you squint closely, then this looks like a scaled version of a periodic central difference matrix. And then you have separated out from that the actual discretization, the numerical fluxes. So the end goal was basically to show that this right-hand side for our finite volume scheme could be rewritten in this form where it's 2 times this matrix Q, which is our periodic central difference matrix here, Hadamard product with this flux matrix multiplied by 1. And what this does is it just takes a Hadamard product of these two matrices and sums them up over the columns. So the factor of 2 is just there for some consistency purposes. But the main theoretical result I'm trying to emphasize here is if I take my finite volume scheme, I can actually reformulate it in this more general matrix form, where I have some mass matrix, H times the identity, plus this Hadamard product term. And this is entirely an algebraic reformulation of finite volumes. And if you look closely, then this Q is a second order periodic differentiation matrix. And the main result that I'm going to rely on is the fact that I don't actually need the structure of finite volumes. As long as I have some matrix Q, which is skew symmetric and exactly differentiates constants, then you can actually show this is an entropy conservative, semi-discretely entropy conservative formulation. What this means is we can immediately generalize this beyond just second order entropy conservative finite volumes. You can do spectral differentiation matrix, you can do high order finite differences, and what we will do is now try to extend things to nodal discontinuous Galerkin. So the big jump, I think, for me in going from finite volumes to nodal discontinuous Galerkin was really in just understanding the matrix formulation of things. And if you're not familiar with discontinuous Galerkin methods, essentially it's a finite element method with high order approximations on each element, where you allow for discontinuities in between each element. So what we'll do is we'll basically derive a local formulation where we take our nonlinear conservation law, multiply by a basis function, and this gives you a Galerkin approximation over each element. To couple neighboring elements together, we'll add this term on the left, which is just going to involve this numerical flux F star across element interfaces. So we can take this to be an entropy conservative flux or something else, which we may use in the next couple slides. One thing that's going to be unique about this presentation is I'm going to focus on nodal approximations. These are also known as collocation type approximations, where I'm going to represent the solution using a Lagrange polynomial basis, and I'm going to choose my quadrature points to be exactly equal to those same interpolation points. When you do this, you get some very nice structure, which allows us to prove positivity preservation and simplifies the implementation. And you can go beyond this, but you lose some of these nice positivity preserving results that we'll show later on. So we're going to use these Gauss-Lobato nodes for our 1D approximation, and we can extend this into 2D, 3D using tensor products. So the formulation of nodal DG methods that we're going to rely on is actually a matrix formulation. And what we'll do is we'll take our DG formulation on each element, map it to the reference element, d hat, and we get the scaling of h over 2. And if we just take this and turn this entire thing into a matrix formulation, you end up with something that looks like this following semi-discrete form, where you have a mass matrix M, some differentiation matrix Q, and then some boundary matrices to incorporate this numerical flux. This mass matrix turns out to be diagonal in this case. That's helpful for us. And then these differentiation and boundary matrices satisfy the following form. This extraction matrix E just picks out the left and the right endpoints, which are going to be the values that we use to compute our numerical fluxes. So the whole connection between these nodal DG methods and these finite volume methods is that this Q matrix satisfies a certain nice property. We can actually show that Q times 1 is equal to 0, and that Q is close to skew symmetric in a sense that I'll show you in a second. But the key idea in bridging the gap between a standard nodal DG formulation and an entropy conservative one is to actually take this flux approximation, which is just Q times this vector of fluxes F, and reformulate it in a way that exposes a numerical flux. So because Q times 1 equals 0, Q is a differentiation matrix, apply it to a constant vector, you get 0. You get that these are 0 row sums. And we can actually take this matrix vector product, it's just going to be a sum over the columns of Qij times F of j, and essentially add 0. So I'm going to add a symmetrizing term F of u sub I, and then I'm going to scale by 2 on the outside and divide by 2. And what this gives you is that this matrix vector product here is actually equivalent to a formulation that involves this central flux. So if we, this actually yields a sort of Hadamard product type formulation. And if we replace the central flux with something like an entropy conservative flux, then we can basically approximate this flux derivative in our DG formulation with this Hadamard product term over here that we saw in our finite volume formulation. And this entropy conservative flux is going to give us some theoretical properties that will lead to entropy stability. So this algebraic reformulation is summarized in the following. Here's our standard nodal DG formulation, and here is the volume term, just Q times F over the element. If I want to derive an entropy stable DG formulation, it's as simple as replacing the volume term by this strange Hadamard product type formulation. And what we're going to do is, in practice, we compute this on the fly. We don't actually form this flux matrix. We just compute the entries and sum up the columns of this Q Hadamard product F as we, on the fly, each time we evaluate the right-hand side. Theoretically, if Q satisfies what's known as a summation by parts property, so that Q plus Q transpose isn't exactly 0, it's not skew symmetric, but if we have Q plus Q transpose, the symmetric part of this matrix is just these boundary terms, then we can show that this following formulation in this first line is entropy stable in the sense that we have a quadrature approximation of the following cell entropy inequality. So this is exactly what you would get if you just were to derive a cell entropy inequality over each individual element. and compute the entropy flux in and out of each element boundary. So this holds for any entropy stable flux, local Lasch-Friedrichs, HLLC, all the standard ones work. So this was done way back in the day. This is essentially just a history recap at this moment. And what got me interested was in 2018, I started working on more general entropy stable modal formulations because I wanted to use something other than these nodal collocation approximations. And we've done a whole bunch of work on network domains, reduced order modeling, non-conforming meshes, which basically use this same sort of general formulation. However, more recently, we've also gotten interested in how to demonstrate that these really, you can really make bulletproof, uncrashable simulations using these entropy stable methods. That is the work that we'll focus on today with these positively preserving entropy stable schemes, specifically for compressible Navier-Stokes. Okay, so what is the dirty secret of entropy stable schemes? I showed you that they give you this nice cell entropy inequality, that they, I didn't actually say it, but they preserve higher order accuracy, at least formally. But what I did not mention is that to actually evaluate these entropy stable schemes, the density and pressure at each of these nodal points has to always remain positive. If you actually look back at the formulas for our numerical fluxes, it turns out they depend on logarithms of density and temperature. And so if you try to evaluate this with negative density and temperature, things crash immediately, and we're back to square one. So the idea that we're going to follow is that we'd like to enforce that each of these nodal values of our approximation stay positive, at least for density and pressure. And we'll do this by trying to reinterpret our DG scheme as a subcell finite volume scheme. It's a little bit hard to enforce both higher order accuracy and positivity. And so what we're aiming for with this subcell finite volume scheme is to at least keep subcell resolution to make sure we can detect variations at the within each element and at least preserve that. So you get subcell resolution for each element as opposed to a limiter which might replace this approximation with like a linear or a constant. And mainly what we will do is we'll take our higher order method and we'll just blend it in a very simple element-wise fashion with a first-order positively preserving method, which both retains conservation and this subcell resolution. So what's required is mainly the construction of a positively preserving low-order method. And what we want to do is to make this look as similar to our original method as possible, because otherwise implementations get fairly complicated. And the idea is that if you have a nodal DG discretization, here I have a 1D mesh. These red points are just going to be cell interfaces. Then you can define something that looks like a non-uniform finite volume method over these same nodal points. So if you interpret each of these points as being a cell center, then you can imagine this to be a somewhat ugly, non-uniform finite volume grid. So what we'll do is we'll build our low-order positively preserving method, starting with a very poor choice of DG scheme. We'll take a nodal DG discretization over this entire mesh, and just for simplicity of presentation right now, I'm going to treat this using these global matrices. So if I take a central DG scheme with central fluxes, then I can rewrite this in a global form for a finite for a first order Euler update, forward Euler update, in this following form. So I just have the forward Euler step here. I'm going to assume that my mass matrix is now diagonal. So I'm just going to scale these terms by the ith entry of my mass matrix. And then I have a matrix vector product that just approximates my right-hand side. This is completely equivalent to a central DG scheme. And this is an example of the matrix Q that we're using. This is now a global matrix. We can show that if you have a central DG scheme, this Q is skew symmetric and that this row sums go to 0. So starting from this, we can basically take this term and add an algebraic dissipation, which depends on this matrix Q itself. So we're going to do essentially algebraic flux correction. This dissipation coefficient we're going to assume is symmetric and that it sums to 0. So it's going to look somewhat like a graph Laplacian, which is why it's sometimes referred to as a graph viscosity by Guirmond and coworkers at A&M. So this looks something like DG with Lasch-Friedrichs types interface fluxes and Lasch-Friedrichs volume dissipation. And the key idea is that if we take this scheme equation 1, then we can actually do an algebraic reformulation into this scheme down here. So we can get that the update UI at each node, the next time step is basically equal to UI some convex combination of the previous solution, ui, and some strange intermediate bar states, u bar ij. And these bar states look like these following. These actually look a little bit like intermediate Lax-Friedrich states in a finite volume scheme. So if this term is positive, we know that this term is positive by assumptions on the time step and this dissipation coefficients, then this is exactly just a convex combination. And if we can show that these bar states are also positive and assume that the previous solution is positive, this means that our next solution, the solution at the next time step, remains positive as well. And the key idea for this positivity preserving scheme is that we can actually determine exactly how much dissipation is required to make sure that these intermediate states are positive. So if we look carefully at this, then you can see that that this is just an average of solution states at our previous solution. We assume that these are positive, so this is a convex combination that will be positive. If this term is small enough, then we can also show that that this won't ruin positivity. And it turns out that the exact size of dij that we need to set in order to ensure that this denominator is large enough, that this term scales small enough, is that these dijs, these graph viscosity coefficients, are larger than the maximum wave speed estimate for most standard finite volume and DG schemes. So we'll explain a little bit what these are. We typically just use a Davis type estimate, a naive estimate, but you can do a little bit better if you see some of Girmon and Popov's papers. So finally, if these intermediate states are positive, then we can show so that if the dissipation coefficient is large enough, then we can show that if the time step is small enough so that this term here is also positive, then we get this convex combination argument and we get positivity of our updated solution. And this actually, if you break it up, it looks a little bit like a standard time step restriction for a Ford-Euler method applied to DG. So this was work that was done very generally by the folks at A&M. Our work was to extend it to compressible Navier-Stokes by basically making this one connection that if we want to treat viscous terms, if we have a stress tau and some heat conduction Q, we can lump them inside some general viscous term sigma, and then a LDG type, or a BR1 type discretization of the viscous terms really is just going to append a discretization of these viscous terms into the conserved fluxes. So you can compute these sigmas using any reasonable DG approximation, and then a Bassi-Roubaix one or a LDG type approximation will simply modify the inviscid flux with these viscous terms. And it turns out you can control the positivity of this resulting scheme using the same dij, the same viscosity coefficient. So now instead of standard bar states, standard intermediate states, you now have intermediate states which also depend on these viscous terms. And Shangsheng Zhang in 2017 showed that you can also prove that this intermediate state is positive if you now choose this dij to be a slightly different dij, to make it the maximum between some special coefficients, beta, and this standard wave speed estimate. And this beta is derived here. It looks a little bit strange, but it basically just incorporates these viscous coefficients in a reasonable fashion and reduces down to just this lambda max coefficient if these viscous terms vanish. So with this, we can basically create a positively observing low-order, first-order scheme for the compressible Navier-Stokes equations. But there's one more step to make this actually practical. And this is work that was done by Pasner in 2021, and it was to actually sparsify your discretization matrices. So when we build this low-order scheme, we add dissipation based on the sparsity pattern of our discretization matrices. And because we use high-order DG matrices, all of these matrices are completely dense. And so what you notice is, this is just for advection, as you increase the polynomial degree of your approximation, you're going from cubics to 8th order to 16th order to crazy 32nd order, then you end up seeing that the solution kind of converges towards 0. So if you have p equals 3, you can see that you have a little bit of a dissipative solution compared with the exact solution, which is given by this dotted line. If you up the discretization order, then that dissipation increases further and further until you're basically getting just a constant. And that's because these high order discretization matrices, they basically apply very, very aggressive globally coupled diffusion in order to ensure positivity in this low order scheme. So the solution, replace our discretization matrices. It turns out all we need is a matrix which satisfies this conservation property, this summation by parts property. And then if it satisfies these two, we can choose any discretization matrix we want and retain the properties that we need for positivity. So we're going to choose these sparsified matrices. These are essentially what you get if you plug in a second order finite element method with just linear hat functions into the nodes that we use on each element, to these Gauss-Lobato nodes. So if we do this, this fixes our over dissipation issues, and we can extend this to tensor product elements in a relatively straightforward fashion. And one of our other contributions was to extend this to simplicial elements because it wasn't exactly clear how to do this before. So we also wanted to create sparsified low-order matrices on these simplicial elements, but there's not really a clear sense in which we can, in this 1D case, you can basically take this discretization over a line and take tensor products, but in multiple dimensions, it's not clear how to sparsify a given matrix. Here's an example of a nodal set that's used for a summation by parts operator derived by Xiwang Xu in 2017. And there's no clear tensor product structure to this. And so we had to come up with another way to construct these sparse matrices. Essentially, what we did was reverse engineer how do we preserve conservation and the summation by parts property. And we basically said we will solve for the skew symmetric part of the summation by parts operator, and we'll assume that this is equal to the difference in the jth and ith entry of some vector, and we can actually solve for that vector. It turns out that solution is basically a graph, the solution of a Neumann boundary condition graph Laplacian problem, which is fairly easy to do and fairly computationally efficient if you simply do it once over each reference element. Okay, so now we have this low order scheme on all types of elements. All we need to do is to blend things together in the appropriate way. And luckily for us, if we just do an element-wise blending in a fairly naive fashion, then things work out. So what we'll do is we'll compute two solution updates. We'll assume that everything is done using forward Euler, and we'll compute a solution update using our high order method. We'll compute a solution update using our low order method, and then we'll just blend them in a convex fashion over each individual element, where we choose this blending factor L to enforce whatever bounds we actually want to impose. The bounds that we're going to impose in particular are going to be what we call relaxed positivity bounds. So instead of just trying to prove that the density rho and the pressure P are positive, we're actually going to try and enforce that the density and pressure are larger than or equal to some factor multiplied by the density and pressure that come out of the low order scheme, so that we're bounded away from zero. And we found that this gives us much more robust much larger time steps in practice. So we'll show you a couple of different values of these relaxation factors alpha. We'll show you that it doesn't really seem to impact the qualitative behavior of the solution. And if we do this sort of blending, then we get a local entropy inequality. This is preserved for element-wise blending, at least for the inviscid scheme. It turns out that it is not actually preserved for the viscous scheme exactly. We also get local conservation, which is preserved if we use the same interface flux for both high and low order methods. So at the moment, this means we're restricted to the Lax-Friedrichs flux or to some other positivity preserving flux like HLLC, but we're hoping to explore ways to remedy this in the future. And that's it. Let me show you some numerical results to show you this actually seems to work okay. So here's the LeBlanc shock tube. This is a inviscid shock tube with a, I think, 6 orders of magnitude jump in the pressure. And if you develop some shocks and a region which is very close to vacuum, you don't expect to get higher order accuracy in this, but we just want to make sure that things are robust. So we try a quadratic and a fifth degree 5 approximation using our entropy stable positively preserving DT method. And we get basically first order accuracy, which is the best that you can really expect in this setting, but it remains robust. Here we've set the relaxation factor for positivity to be 0.5. And we can also run this for a viscous shock tube at Reynolds number 1000, and things seem to work. We get about 2 points rate of convergence of 2.7 for degree 2, and we get something like a little bit suboptimal, like a rate of about 3 for degree 3. But this is also because we're really not getting into the asymptotic regime for these. We're just now getting into the asymptotic regime for this finest set of meshes. And I should note that this viscous shock, it has an analytical solution, but we're running it at a much higher Mach 20 number just to make sure that we're actually generating positivity violations to really test our scheme. We can try this in 2D with an isentropic vortex with density 10 to the negative 3. This actually generates positivity violations for a standard entropy stable scheme, and things seems to work okay. We get about order h to the n plus 1 for degree 2. We don't quite get it for degree 3, and we get something a little bit weird for degree 4, but we're not reducing the accuracy down to first or second order. And then we get similar behavior for triangular meshes as we do for quadrilateral meshes as well. So this is mostly verification to make sure we're not ruining things when we introduce this positivity limiting. Let me show you how this behaves on a couple more standard test problems. So here's compressible Euler, where you have the double Mach reflection. You have, I think, Mach 10 flow that basically hits this reflective boundary condition at the bottom and produces this nice wave and this beautiful little vortex structure and this triple point shock at the end. So things resolve pretty well. We used relaxation factor of alpha equals 0.5 and ran this up until t equals 0.2, and everything remains stable. And what was interesting to us is that we get very good agreement with other methods in the literature. This is actually from Pasner. Unfortunately, it seems like the reference is cut off. Pasner 2021 solved the same problem using a invariant domain preserving DG method, which also preserved positivity but enforced a different entropic stabilization. And for a much higher resolution, he uses 600 by 2400 elements. We use 250 by 875. We seem to get similar resolution of these vorticular flows. So this was encouraging for us that we don't seem to be adding a lot of dissipation in this scheme, and it seems to be behaving fairly well for these under-resolved simulations. We can do the Sadov blast wave. I'm going to skip over this because I think this is relatively straightforward. We can also add a little bit of shock capturing using this just by varying our blending coefficient. And I'm going to try and talk a little bit more about the compressible Navier-Stokes Daru-Tenod shock tube. So this was interesting to us because the folks at A&M were they constantly talk about this problem because it's a little bit questionable what exactly the reference solution should look like in the literature. So this is a reference solution from this paper in 2022 of a overkill, highly resolved 512 million node mesh. This is Reynolds number 1000. And what you basically have is a shock that moves towards the right and then bounces off a viscous wall on the left and drags against a viscous wall on the bottom. And what happens is you get a boundary layer which forms, and as the shock bounces back, then you get this nice vortex structure and this beautiful shock boundary layer interaction behavior. This is using a invariant domain preserving scheme for a second order invariant domain preserving scheme for the Navier-Stokes equations that Guirmond et al. Developed. And this is our entropy stable method with degree 3, 600 by 300 grid, a more under-resolved high order entropy stable approximation. And this is where I believe entropy stability might come into play a little bit. The entropy stability improves robustness of your schemes, but it also tends to be important for convergence to the appropriate viscosity solution of these nonlinear conservation laws. So what's remarkable to us is that you see very similar shock structures. You can see that there's this nice little branching behavior over here. You see oscillations in the shock here, but despite this, the fact that we haven't resolved these oscillations, we're still getting really good qualitative agreement with all of these, with all these other features that we see here. And what was a little interesting to us was that some of these features appeared to be really sensitive to shock capturing. And when we removed some of this shock capturing, it seemed like we recovered more of the features that we saw in this reference solution. So this is, again, our solution on the top left. Sorry, Eric, for using your paper in this way. But this is essentially matching our reference solution. If we drop the degree down to 2 and we coarsen the grid slightly, you can still see very similar shock structures. You have this, you have the same type of branching behavior over here. You can see a little bit more oscillations. The solution looks uglier, but the qualitative features look roughly the same. And if we suddenly add entropy stable shock capturing, this is from Henneman and Gassner in 2021. This is essentially using a parallel of Pearson's shock indicator, this modal shock indicator, to apply viscosity in a fairly conservative way. Then the shock structure completely changes, and you, instead of getting this part which branches out over here with these two shocks coming off, you now see that this shock structure kind of just branches directly down and looks qualitatively different. This little bubble down here also looks a little different. And we noticed something similar with some other results in the paper, not just Stanick and Wood-Erden, but also older results from Yi and Sjogren, as well as some other shock capturing based simulations that we found elsewhere. So we're not sure which one is the correct solution still. I don't think there's an agreed on reference solution that everyone in the literature, everyone in the community considers correct. But what we have noticed is that this shock capturing seems to play a really big role in changing qualitative features of the solution. This is a higher Reynolds number. Reynolds number equals 10,000. And what I'm going to do is vary this positivity, this limiting parameter alpha, which controls how aggressively we enforce positivity. If I change from alpha equals 0.1 to 0.5, you see some differences in this flow. It's highly under-resolved and chaotic, but overall the shock structure looks kind of similar. If I apply shock capturing, then you get a vastly different solution in terms of the qualitative behavior. And so this is what makes us a little suspicious of our shock capturing type results. And our goal with this was to basically produce a positivity preserving method with minimal dissipation to avoid exactly this type of behavior. Okay, so I'm going to try and wrap up with just a little bit on some recent projects that we worked on, which is to extend these entropy stable schemes, is to construct these entropy stable schemes in a completely new way. So previously, we've been relying on this Hadamard product formulation, where we introduce these entropy conserved numerical fluxes and then build our scheme from that. This is really advantageous, but has some limitations, especially for more complex problems where you might not know the form of these fluxes explicitly. So what we'll do now is we'll actually try to enforce this cell entropy inequality that you get from these higher order entropy stable schemes through a limiting process. And we'll try to do limiting in such a way that is minimally dissipative. So previously, for our positively preserving limiting, we had subcell resolution in the sense that we interpreted our Gauss-Lobato nodes as a finite volume subcell. However, we were doing element-wise blending. We just took a high-order solution and a low-order solution and blended them with some constant blending over each element. But you can actually do this blending in a subcell fashion as well. You can blend more in one area of an element than another. And the way to think about this is to think about finite volume-based blending, where you take the interface fluxes at finite volume subcells and blend each of those in specific ways. So you have to do this carefully to ensure conservation, but if you do this, you can get a much less dissipative scheme, as we'll try and demonstrate in a little bit. What we found also was that when we try to do this sort of blending, it was a little difficult to preserve entropy stability. And when we tried to do it, preserve entropy stability in certain ways, it turned out that not all the ways would preserve high order accuracy. So let me try and explain what we were doing. Our motivation for this was to see what happens if we try to jettison the framework that we worked with for all these years. What is instead we take a possibly non-entropy stable, just naive nodal DG formulation, and we'll write it out in this semi-discrete form over each element. So I'm just introducing this R sub I. This is going to be the residual or our volume integral over each element. And we'll assume that this scheme is conservative so that these entries of the residual R sub I sum to 0. That is the only assumption I'm going to make. What we can show is that this is algebraically equivalent to something that looks very similar to a finite volume scheme if you introduce these reconstructed finite volume type fluxes. And this was an observation, again, that Will Pasner made. He has done a lot for our research group, so thank you, Will. If you define these reconstructed finite volume fluxes to be the numerical flux on the left and right, and in the middle to be partial sums of these volume residuals, then it turns out you get this algebraic reformulation. These two are entirely algebraically equivalent. So we can make our standard DG method look something like a finite volume type scheme, where M sub I is going to be just a stand-in for this cell width. And then we can do finite volume type limiting on this algebraic reformulation. So what we'll do is we'll do this finite volume reformulation of both high and low order fluxes. We'll take the right-hand side from our high and low order schemes, do this algebraic reformulation, and then we'll blend these fluxes together in a convex fashion over each subcell interface. So on one DG element, you'll have subcell interfaces between each node and also on the boundaries. Again, blending coefficients should be between 0 and 1. 1 will recover the high order nodal DG method, and 0 will recover your low order invariant domain preserving or positivity preserving scheme. And the trick that we were the trick with this most recent work was trying to pick these limiting factors in a way that enforced entropy stability in an appropriate fashion. So because these limiting factors are now varying over the entire element, for technical reasons, when you choose these limiting factors, you actually lose entropy stability. It doesn't preserve a cell entropy stability that we get from either our high or our low order scheme. So you can blend these together, but then you no longer have a cell entropy inequality, and we had to reinforce this in a certain way. So we tried enforcing a couple different things. We tried enforcing a minimum entropy principle. This is a really common approach where for an inviscid flow, at least, you get robust entropic schemes if you enforce that the entropy at each node is larger than or equal to the minimum entropy, this is specific entropy over each neighborhood. We also tried enforcing a semi-discrete version of this entropy stability condition from Tadmor over each subcell flux. And in both cases, we observed something was strange. We tried degree 2, degree 3, degree 4, and we always seem to recover low order, first order convergence. If you use this second condition, I think you get second order convergence. And if you relax this first condition, which is commonly done, you also get second order convergence, but no further. So neither of these pointwise approaches retain higher order accuracy. And what Yimin had figured out was that it's actually possible to enforce a cell entropy inequality by choosing these limiting factors together in a bulk fashion, in a coupled fashion over each element. So what I have on this top line is the entropy balance over each cell. This is essentially the time rate of change of entropy over a cell. And on the right-hand side, this is all of the rest of the terms, all the interface terms that you see on the boundary of an element. So what we'll try to do is actually to enforce this semi-discrete entropy inequality over each cell by choosing these limiting factors in a clever way. So you end up getting a optimization problem, which has a very specific structure, but more importantly is if you take degree 2, degree 3, degree 4, then you suddenly see that we're no longer restricted to low order accuracy. We get rates of 2.74, 4.28, 4.36. We're not getting perfect high order rates, but we do seem to, again, achieve high order accuracy. So what makes this actually feasible is that when we enforce this cell entropy inequality, it gives us one particular inequality constraint. So I'm going to use this notation where these interface fluxes are given as functions of these limiting parameters. They're convex functions, and these are both, importantly, linear functions of these limiting parameters. So if we take this constraint, we basically want to enforce that VI transpose times the difference of these fluxes is less than or equal to the jump in the entropy potential across boundaries. And if we translate that into an algebraic program, this actually looks like a continuous knapsack problem from optimization, linear programming. So you want to maximize the sum of these limiting factors to make it so that limiting factors are as close to 1 as possible, such that we have one single inequality constraint, which is equivalent to this entropy condition that we're enforcing here. And then we have some box constraints on our limiting factors where we can choose this upper bound to be an upper bound on the limiting factor that is necessary to ensure positivity. So basically, the limiting factor has to be small enough so that we ensure positivity, and then we try and maximize it to ensure cell entropy inequality. We can solve this efficiently with an order n log n solution algorithm that basically just involves a sorting of this coefficient vector AI, which shows up here. And what we see is that it works pretty well. This is an example of several different discretizations for the solid shock tube, just to show you what happens when you don't apply any entropic principle. If you use standard nodal DG, which we'll refer to as DG-SEM for DG spectral element method, then you end up with this entropy glitch in the middle of this rarefaction wave over here. If you look at entropy stable DG, DG-SEM plus a minimum entropy principle, and DG-SEM plus a cell entropy inequality, none of these experience this entropy glitch. But we know that this minimum entropy principle is going to be low order accurate. So one of the advantages of this is that we can now apply this to more to different problems without having to change quite as much. We don't have to derive a special flux for different problems. We just have to know what the entropy is and what the entropy flux is And if we look at the KPP problem, then we can, this is a pretty well-known scalar conservation law in 2D to test entropy stabilization. If we apply shock capturing, which is necessary to basically deal with discontinuities along this spiral line, then you get a solution which looks like it is converging, but has these sort of weird artifacts. You can kind of see mesh. You can see the mesh show up inside this solution, and these artifacts don't go away as you refine the mesh. If you enforce shock capturing and also apply a cell entropy inequality, then you get this nice behavior, and it converges smoothly. It converges as we refine the mesh. If we look at the Kelvin-Helmholtz instability, things also seem to work. I just want to point out that there are some strange differences between entropy stable DG and DG SEM. This is using our new cell entropy inequality that we're enforcing using limiting below. And especially as time for long time simulations, the solutions can look really qualitatively different. But this is, I think, in my opinion, due to the sensitivity of the Kelvin-Helmholtz instability. And then finally, to show you a little bit of how this behaves for a more challenging problem, here's a Mach 2000 astrophysical jet. Here's standard DG-SEM with the cell entropy inequality and positivity. We can also replace standard DG-SEM with ESDG. We can use an entropy stable DG method as our baseline scheme. And then here's our old method where we use element-wise blending of for positivity. You can see it on these two, when we enforce the subcell inequality, you get lots more nice, I guess, vorticular features, but you also get a little bit of this carbuncle effect at the tip of the shock. This actually vanishes if you use element-wise positivity preserving limiting, mainly because it adds more dissipation. So this is not an entropic, this is not a violation of entropy stability. I think it's just not enough dissipation. You can remedy that using whichever approach you'd like. So with that, let me go ahead and stop. Thank you for your attention, and I would welcome any questions that you have.
All right, thank you. Was an awesome talk. Do you mind unmuting?
Yes, give me a second. Sorry, I went a little bit overtime.
No, you're good. You're good.
Is it up here?
Just so we can hear.
Okay. Okay, perfect.
All right. All right. Questions for Jesse? A lot of really cool things. Sorry?
Great talk, super interesting.
Thank you.
I have a couple questions.
Sure.
So for the entropy stable PG, just the baseline,
Yeah.
are you satisfied that entropy inequality represents an element, or
Yes.
you also satisfy the stable and what they call base points?
We do not. No. Yeah.
And then does it matter what you choose? Or is there
It's an excellent question. Yeah. Yeah. We at least for the compressible Euler equations, we only use the Navier-Stokes entropy. Yeah. Exactly.
for your subcell extent?
Hmm.
You cut out that off the back.
For the subcell scheme.
Like when you do the limiting, you put the damage.
Yes. Yeah, you mean the
The obsession factor.
Yep.
Is that, like you said that for one, you just use,
we actually never tried one, believe it or not. We've only set it to like 0.1 and 0.5. 0.1 to be really, we mostly just wanted to ensure that we weren't getting clipping or anything. I haven't tried 0.1. I'll let you know if we can run that.
Oh, sorry, like one, but there's one that's just like straight.
Yes, yeah, exactly.
And that's, I guess it would be great accuracy going, it would be like, you pick that.
Potentially, but it's also so there's two aspects of this. It's if you choose one, you sharpen, then you get a more sensitive bound, but that bound's still only activated if you ever have these positivity violations. So that's one difference that from other limiting schemes that we tried to look into. So instead of enforcing like a TVV bound or detecting other types of violations, we just look for positivity, and this usually isn't enough to stabilize things. Without some other entropic stabilization.
Let me just follow up on
Please,
this.
please.
About the zero.
Then our time step goes to zero. So what we'll observe,
It does.
absolutely, yeah. So we calculate the time step at each. We calculate the time step size at each iteration to enforce this positivity bounds. That's a requirement for provable positivity preservation. And what we'll observe is that time step will start large and just kind of decrease to zero as our pressure and density get closer and closer to zero. Yeah.
So you basically just put like a little some slot out or something like
Well, yeah, we choose that using just alpha, setting alpha to be something like 0.1 or
So it's relative.
Yeah.
it's a
relative.
the relative. Yeah, that has proved to be really important for us. When we first tried this using like Zhang and Shu's limiter,
that.
yeah, it's tough. I mean, I think it works well if you. I'm not sure how they do it. I think they have some TDD limiter on top of it, but for us, we just saw that the time step always converges to 0.
I like going with you, but very awesome. So,
Please.
a couple side we show that compare with values.
Yeah, yeah. Yeah, sorry about that, Tarek.
So I was curious, is the color bar the same as these papers?
It's okay. So the color bar is the same for these three, which is why you kind of see thicker lines here. So this is a numerical slur, and they basically take the absolute value of the gradient of density, and then they apply some weird exponential transform. We matched the color bar from basically this paper. So that was our reference. I'm not sure, Eric, wait.
Same thing.
Okay.
So that's right, I don't think that.
Okay, fair enough. Yeah. That's just because we didn't realize we could make our background in Paraview white until after we published the paper. Yeah, that's our mistake. That's just a visualization thing.
I have a related question.
Please.
So this going back, you said that the results for download. Yeah, they're being similar. Is this because this is the truth, or is it because you share some similarity in your approach?
I am not sure. Jean-Luc always says that at least for this problem, we don't know if it's a truth, but he gives evidence that this is grid converged. So in his approach, he's able to refine much more finely because we actually have a little bit of a parabolic time step restriction, so we can't refine the mesh too much relative to Reynolds number. He does not have that restriction, and so he's able to do an overkill mesh. And what you actually don't see is that there's actually a boundary layer. The mesh gets smaller near the boundary to capture these viscous phenomena. So what he shows is if you take the solution, it doesn't seem to change as you refine the mesh, and neither does the skin friction coefficient along the boundary. So that's, I think, the only evidence we have that this might be the right solution, and that it doesn't move as you continue to refine. Yeah, I asked Shogreen about that, and he said I remember we reported that was grid converged, and then he said I'm not sure. Well, I think he also said it's been maybe like 13 years or so, and so he wasn't entirely sure. But he said there might have been some jumping around still. I think the lesson we took from this one was just it is a notoriously sensitive problem. And actually there were some cases where we actually changed the order, and depending on how we changed the order and the mesh resolution, we would jump between what looked like the grid converged solution and a completely different solution.
You know about insurance, so you guys are supposed
No, they are enforcing a minimum entropy principle on the inviscid term only, and then joining that together with the Navier-Stokes terms. I don't think, to my understanding, they're completely coupled scheme for the inviscid and parabolic equations does not actually enforce any real entropy principle. It just enforces positivity of internal energy and density.
Let's try to give a chance to the people online to ask a question. Please pick up if you have any questions.
Hi, Jesse.
Hello.
Great talk. Thank you very much. I have a general question regarding the entropy stability of the DGSEM. So the way I see it, you derive the entropy conservative flux based on Tadmor's condition. And then to make it entropy stable, you add dissipation. Is that right?
That is absolutely correct, yes.
Okay, so this is all with respect to a particular entropy pair, right?
Yes,
so
that is correct.
If you want to enforce entropy stability with respect to more than one entropy pair, is there a way to do that as well?
Yes, absolutely. Excellent question. So I think it may be specific to our choice of low order scheme. If we use Lax-Friedrich fluxes, then I think we get this invariant domain property, which is necessary for this. But what you can do is if you solve, so for each entropy pair, if you solve this optimization problem, then you can simply take the minimum. You can solve this optimization problem for every single. Sorry, let me see. Actually, give me 1 second to make sure. Uh, yes, you can enforce multiple entropy inequalities, but it essentially will do it by a greedy approach where you take the dissipation to be you take the smallest set uh, of of limiting coefficients. So if you have one, you can solve this optimization problem for one entropy, and then take those limiting coefficients and set them as bound constraints, and then solve a second optimization problem for another entropy, and then you're guaranteed to enforce both entropy inequalities, but you're doing so by essentially adding more and more dissipation. Does that?
Yes.
Okay.
Yes, of course, but I mean, for some problems, it might be necessary.
Yes, absolutely.
Right. Okay. Thank you very much.
Can you just combine the products?
Unfortunately, no, because so this to get this nice efficient solution algorithm, we have to have only one single inequality constraint.
Get a solve an optimization solver.
If you-
two constraints.
Yes, that's right. If you're able to account for two constraints, then yeah, that would be absolutely fine, and you could do it monolithically and probably get slightly better, slightly larger limiting values that are less dissipative in that case.
I do have a question about this. Is the sum of LIs what the one?
It is what we can get.
No.
Yeah.
But if you could, what is it? The minimum is maximum, or some other ones of the?
That's a really good question, and I don't know. So the reason I'm not entirely clear is because the LIs they factor into our equation in a way that's very, very discrete.
Mhm.
So I don't know if they actually have a continuous analog. I don't know how to interpret them in a variational form. And so we just chose, yeah.
Yeah, sorry, I didn't mean to.
No, it was actually a follow-up based on your question, Sanya. So I'm not entirely sure because this was a bit fast for me, but your limiting approach, can you
Yes.
think of it as a semi-discrete or a fully discrete approach?
Excellent question. Yes. So at least for the cell entropy inequality, it is completely semi-discrete. We need fully discrete for positivity, but yeah, this specifically is just semi-discrete.
Okay, great.
Thank you. Sure.
So we can basically decompose your cells.
Yeah.
If you use a high order, like positive shorts, you do have a PDB.
Absolutely. So this is work that we didn't do because Gassner and Reda Ramirez, and I think Will Pasner actually, he is very involved in this this limiting world, or was. They basically took the subcell decomposition and then used second order schemes. They investigated a whole bunch of different second order finite volume schemes for the low order baseline, as well as different choices like HLLC versus HLLE versus whichever flux you'd like. Yeah, and they showed it does seem to improve things. They used the minimum entropy principle for entropy stabilization back then. So I don't know. Yeah, still first order for those problems, but I think I don't think it goes to necessarily first order. It goes to the order of the baseline scheme, and then I don't know how relaxation might factor into that. But it does qualitatively improve things. Shocks get sharper. Oscillations, or sorry, vorticular behavior gets more vorticular.
I have a question on this actually too.
Yes.
So, do you just interpret the nodal degrees of freedom as averages? No,
expression.
Yes. This is conservative. Yes. so you can interpret them as averages. We really just do this at an algebraic level. But yeah, it remains conservative. So it remains conservative based on the way you decompose the residual. So if you basically isolate the conservative part of the residual, so in this case, DG, it would be the part of the variational form that's integrated by parts, so that it disappears when you.
And to clarify,
Yes,
what I mean is,
sure.
Is the integral same? The integral is zero.
Yes, it is this.
The sum of the.
Yes, the integral is the same, and you pay for it in terms of accuracy because these are not exactly cell centers.
Thank you.
Yeah, absolutely.
Wait, so is the element like
Yeah, that's right. Yeah, exactly.
the
Yeah, so this is a little bit misleading over here. Really, really we are just taking the last element to be from here to here, and so it's really not the cell. It's really not the cell center. It's just the left side of the cell for this element. But the size of each of these subcell elements is exactly the same as the Lobato weight.
Yeah, it's not the cell center.
It is definitely not the cell center.
Okay.
We interpret it as a cell center.
I understand.
Yes, hence the accuracy issues.
Yeah, stepping,
Yes, but that's also, so that ties into why. No, I think it does matter, but I think it also depends on how often you activate your bounds, which is why we try and choose the weakest possible bounds just to make sure we really we do see the cell the stair casing a little bit more if you enforce something like a maximum principle or maximum minimum principles or TBD bounds.
Okay. We still have a few folks online, including Dr. Wolf Asner that didn't mention
Oh.
terms. Any questions from the folks online? So Jesse, for all of this, the mass matrix needs to be diagonals because
Yes, so we can.
that's a requirement.
That is unfortunately a requirement. So, thanks, Will.
Okay.
I appreciate it. Thanks for all the work that you did to basically get us so that we could use it to get to this point. So yes, for entropy stability, we can get away with pretty much any discretization. Dense mass matrix, we don't really need a particular structure, but for limiting and for positivity preservation, that really does seem to require a diagonal mass matrix and also this collocation assumption, including having collocation points at the endpoints. Yimin worked several weeks on an extension to just trying to change the nodal distribution so that we use Gauss points instead of Gauss-Lobato because this is more accurate. And it is much more technically difficult to ensure everything is both entropy stable and also positively preserving. Although with this new approach at the end, we might go back and look at that because a lot of that trickiness was related to the entropy stability formula, the entropy stable formulation.
And then just another thing to clarify.
Yes.
The positivity is enforced at the degree rate.
Absolutely, yes.
And this is not about percent basis. You don't have positivity in other points.
That is correct. Yeah, in between you can dip negative.